All right, so let's take a look. So now some other stuff, aspects of Windows services. When you start a Windows machine, it launches a whole bunch of processes before you even log in. It has to. Processes to like read the keyboard and take key presses from you to log in, for example. So these are generally services, and they generally run with one of the accounts that's there before you log in, like system or net services or other things. There's a variety of accounts that are used by the system itself to run processes. And by the way, this is a huge security problem at every enterprise, and also in the cloud, are these service accounts. Most of the accounts are not a human that logged in. They're a process connecting to another server to like fetch, to check, see if something is running, to send a signal, and those things never have two-factor authentication. In fact, nobody's ever figured out how to give them two-factor authentication. They have like a hidden password that is typically never changed, and this is how bad guys often get in. They compromise a service account. Now they can log in and launch a process with the service account, and then they don't show up in your monitoring tools. This is actually a very common flaw these days, all these service accounts. Anyway, that's how it works. And so a system account is the most powerful account of all, more powerful than the administrator. And this is where you'd like to run as. And as you probably know, if you use Metasploit, this is often what you do. You get a shell, but you're low privilege. Then you try to escalate to administrator. Then you try to escalate to system. And if you get up to system, you can do things like change the password hashes and things like that. Right. And so here's a handle to the service control manager. That's the API call. You can create a new service and start a service. And you can have the most common type of service is share process. It stores code for a service in a DIL and combines several services into a single shared process. If you look in Process Explorer, you will find a bunch of these SVC host things running, using the same executable to launch a bunch of services. And if you hover over one, it will show you, like this one here is running what looks like about 10 Windows services in one executable. This is all specified in the registry. This is what like the 100 services are. They're all SVC hosts, and each one of them is running like 5 or 10 things, and that's all the background services that are available to provide service to your programs. So here's one that runs as an independent process, and here's one that loads code into the kernel, other kinds of services that are out there. So they're all specified in the registry: HT, local machine, system, current, control set, services. And when you go in here, here's all the services: bits, browser, everything here. All the services are here. There's hundreds of them, alphabetical, and each one of them has information here. Like here's the path to the image, and notice this is an SVC host one. It's going to run SCV host with this command line switch to terminate it, and then it's going to have other information about the parameters it runs under here. So that's what's in the registry, all the information about the services. And the SC command is the command line tool to control it. You can use SC, and you can then query about the browser service. It will tell you about the browser service. This is just a printout of the data that you just saw in the registry, made a little bit more human readable. And all right, so those are services. Now, for some reason, there's another thing that's not like, now libraries and services and processes are all different, but they're quite similar. And there's another thing called comms, which are like services, but a little different. So a COM is a way to share code between objects. You can write a component object model object, and every time you try to use it, you first have to call an initialize function first. By the way, the same thing's true of a DIL. You have to call a special part of the DIL to prepare it for use. You have to call this initialize function before you can call the other COM libraries. So COM objects are accessed by globally unique identifiers with various names, and they're long 128-bit objects. All right, and so that's what they are, another software object in your Windows machine being used. And then there are exceptions. When exceptions are like interrupts, something happens which sends a signal which tells the processor, wait, you have to stop what you're doing and do something else. Something important has happened. Like somebody's pressed the off button, it's time to shut down, or something like that. So when an exception occurs inside a program, then it calls the structured exception handler. That's not the off button, that's when your program is running and it does something that is forbidden, like it tries to write to an invalid memory address or execute a command in user mode that is only available to kernel mode, or anything like that. It tries to execute the instruction, and for some reason it cannot execute the instruction. It then raises an exception. And what first transfers the code to the exception handler. So that's at this location called FS0. FS is a register. And so you'll see here storing exception handling, and here is code that's writing into the exception handler. It's moving data into the FS0. This is malware writing data into the exception handler. This is one way to get control of the box. You change the exception handler, and then you cause an exception. That's one way to get control of the box. We'll do that in some later projects. In either this class or 127. I think it's this class, but I forget. It's 127, I think. Anyway, so kernel versus user mode is the other basic thing. The hardware actually has 4 privilege levels. Applications have the least privileges, and the kernel has total privileges. And in principle, you could have devices at ring 1 and 2, but nobody uses them. No modern operating system uses them at all. They just use ring 3 and ring 0. And now, not shown in this diagram, they use something they call ring -1, which is hardware-assisted virtualization. So your virtual machine can have access directly to the kernel. Now that's, anyway, but within one operating system, you go from 3 to 0. All right, so nearly all code runs in user mode. Everything you launch from a command line or from the start button from your desktop, that's all in user mode. And therefore it all runs with your permissions only after you've logged in. And that's where you normally live. Everything the user does is in user mode, because if you crash something, like you crash your browser, it will just stop the browser, but the computer keeps running. It can pop up a message, you can restart it. If you crash the kernel, the whole machine dies with the blue screen of death. So normal users are not supposed to be messing around in the kernel. That's why you have user mode. It's like a safe sandbox for you to play in. That's the idea. So each process has its own memory, its own resources. If it crashes, it just stops that one process, but the other processes keep going. The machine is still running. You cannot jump directly from user mode to the kernel. You have a special command just to call predefined functions. There are only certain kernel functions available, and you have to use those. And so you call, this is one of the assembly language and commands, there are various different ways to express it, but those are what goes into the kernel. All right, so kernel processes. They all share resources and memory addresses, very few security checks. If any of them use an invalid instruction, the whole OS dies with a blue screen of death. Antivirus software and firewalls patch in kernel mode. At least they used to. I'm not so sure they do now, but they used to, and I'm working on, that's why we don't have rootkit in this class anymore. I used to. I had some old rootkits that ran by patching the kernel. There's a new technique they use that I just learned about a couple weeks ago, and I'd like to add a project. I may not be able to get to it this semester. There's a patch you can make in userland now. Microsoft has been trying for decades to push everybody out of the kernel, because it used to be all the antivirus products and firewalls and everything would put code in the kernel, and all the device drivers would put code in the kernel. And Microsoft got so fed up with this, in Windows XP, they finally made Windows error reporting. So every time your machine crashed, it would tell Microsoft why it crashed. And they found out that more than half of all the crashes are caused by this third-party code in the kernel. And they said, you know, why are we letting every idiot put code in the kernel and crash the box? We should make everybody do whatever they're doing in userland, and we will control the kernel with higher quality code. So they've been pushing all these products out of the kernel gradually with versions of Windows. Anyway, you can put malware in kernel mode. There used to be kernel mode rootkits. They were pretty common. And I suppose they still exist, but they're a whole lot harder to make than they used to be. As I said, I couldn't find an example to put in this class for the last few years. But it would be nice. That was the way it used to be. Now I think they're pretty much all in userland. Anyway, all right. And then there's the native API, which is pretty amazing. I just talked about the normal API with API calls. There is a special API that was not intended to be used by any developers outside Microsoft. It was for internal use only. But there's two problems. One is information leaks out of Microsoft because people go in and out. The other thing is you can just put it in WinDebug and you can see the entire operating system in assembly code and just read it. It's not that hard to do. They can't hide anything from you, not really. You don't have the source code, but you can figure out what the API calls are just looking at the functions. So this is what malware writers often use. So here's what happens. You normally use your application is here. When your user application accesses the kernel, it's supposed to load kernel32.dil, which is not in the kernel. It is your gateway to the kernel. Remember the general rule, everything in Windows is always named the opposite of what it is. The thing named kernel is not in the kernel. It's in user land. And that doesn't go directly to the kernel. It goes to this thing called ntdil.dil, and that makes the jump to kernel mode, and it touches the kernel. This is what the kernel is. The kernel is a single executable file called ntoskernel.exe. That's the kernel. That's loaded into memory when you boot up, and it has to be in memory all the time you're running. And it has other data structures here, like device drivers. You have them and stuff. This is what actually does the kernel. This small object always in RAM, and you reach it normally by calling kernel32, which then calls ntdil. All right, so ntdil is the native API. Normal programs never call ntdil directly. They access it by means of kernel. But you could bypass kernel32 and go to ntdil, and then you'd be writing a program not like a normal developer, but like a Windows operating system developer. Normally, only people at Microsoft would be doing this direct call to ntdil. They'd be writing things like this library here. So that's another thing. So it's undocumented, intended for internal use, but information has leaked out about it. And of course, the calls can be more powerful and stealthier because, of course, anything this program does, it does by calling ntdil. So clearly, the abilities of ntdil are going to be a superset of the abilities of this file here. So you have more granular control. It's like the raw sockets. The raw sockets give you more control over networking than the higher level calls that will just let you do the standard things. So your security programs often try to hook information going into kernel32. So if it is at this level, then you can fool it by just not loading kernel32 and making a call directly down here. Sometimes that will bypass your endpoint protection products. All right, and so here's some common native API calls. Query system information, query about a thread, query about a file or a key. These give you much more information than the Windows 32 calls. You have much more details available. And so another one is ntcontinue, which returns from an exception. So these are just some calls you could use to go direct to the native API and help confuse malware analysts and confuse the security products. Just doing anything in the non-standard way is, of course, more likely to slip past defenses. Let's try another Kahoot. I think it's kind of funny. I got a friend I know is going to mock me for going to a protest, but it makes you feel better. You feel like you've done something. And of course, you can argue it doesn't matter. I don't know. I think it does matter. Of course, you're only one of millions, but you know, it's. I think it matters. I'm going to go to FedEx tomorrow and try to make a nice sign, so we'll see. $372-5619. You know what would really do it would be if he had a general strike, but nobody ever does that in America. That's what the French people say we should do, and I think they're right. That would do it. If we shut down the whole economy for a day, they would notice that.
I'd be happy even for a general strike within a company.
Yeah.
Like it happened with the automotive industry.
Well, that does happen sometimes, well, not that often. But boy, a general strike would be justified under these conditions, I think. But I don't think you can do it in America.
Forgive me, Sam. What did you say? So NTDIL gives a more granular control.
Yeah, that's the native API.
It's the native.
Yeah.
Because it's the native.
Yeah. Good. All right. Let's give it a shot. All right. Which user account is more powerful than the administrator? Yep, system. It's the most powerful. Root is Linux, not on Windows. It's system. All right, what's the service that loads ring 0 code? kernel driver, of course, in the kernel. Good. All right, where's the native API? Yep, NT-DIL. That's it. NT is new technology. That was Microsoft's upgrade from the MS-DOS-based system. Windows 95 and Windows 98 and Windows ME were still running MS-DOS behind the scenes. They were basically a graphic environment on top of MS-DOS. And in 1993, Microsoft rewrote it and made the new technology, Windows NT. And that was the one that led to all the modern versions. That's why they had.
So Windows NT was Windows new technology, not
Right.
Windows Network.
Right. That was when they finally got rid of MS-DOS and rewrote it all, starting over. All the rest were just layers on top of MS-DOS. Yeah. Yeah. All right. And what happens when a divide by zero is attempted? Yeah, it's an exception, so it goes to the exception handler for whatever program tried to do that. And then, if the exception handler doesn't handle it, then it goes to the operating system, which will pop up some generic message like your program has stopped, something like that. All right. So I think I already know who won. So. Yep. Oh, good. All right. Now, I did plan to demonstrate something today. Let me see if that 304, yeah, 304 is pretty easy. I think I can do it in, even though I only got 10 minutes, it's probably enough. Because my Windows machine is already up and it's already ready to go. So let me just start another recording.